Hi everyone. Today we're going to be talking about Ceva's theorem. This is a very powerful theorem that explains a lot of other useful facts in geometry. And if you have some experience with geometry, you might have been relying on this theorem without even knowing it. To see this, let's first talk about what a Cevian is. A Cevian is any line that goes from one vertex of a triangle to the opposite side of that triangle. Now, you might recognize the famous lines known as medians, altitudes, and angle bisectors are all Cevians. And you might know that the medians of a triangle are all concurrent, meaning they all intersect at the same point. This is also true of angle bisectors and altitudes. And these facts then go on to serve as foundations for other discoveries in geometry. And at the base of all of this is Ceva's theorem, which we're going to talk about today. Now, Ceva's theorem and Cevians are named after this guy, Giovanni Ceva, an Italian mathematician who published the theorem in 1678. But I think it's important to give credit to the true earliest known discoverer of the theorem, and that is Al-Mu'taman. And he, forgive me if I butchered his name, but he was a scholarly king who ruled in Spain from the years 1081 to 1085, so that's the 11th century. He studied astrology, philosophy, and of course, mathematics. He wrote the first known formulation of Ceva's theorem, and he put it in what he titled a book called the Book of Perfection. And this was written almost 600 years before Giovanni Ceva discovered Ceva's theorem. And it's unknown whether Giovanni Ceva independently came up with the theorem or if he found a translated version of Al-Mu'taman's book. But perhaps in light of this, we should rename the theorem and rename Cevians after Al-Mu'taman. So, with that background established, let's get to the theorem. Now, a general overview of the theorem is summarized as follows. So given this triangle, A, B, C, with points D, E, and F along the sides, now we're going to see that Cevians are going to be made if we get a line from A to D. So a line from the vertex A to the side across from A, which is going to be at point D, line AD is a Cevian for ABD. Similarly with CF and BE. So these are all Cevians. So we're going to see that these three Cevians here are going to be concurrent, meaning they're all going to intersect at one point if and only if the following equality holds true. So we're going to see that this is the equality. The line segment AF divided by the line segment FB multiplied by the line segment BD over DC multiplied by CE over EA is going to be equal to 1. So only if this equation holds will all three of these Cevians be concurrent. And the order of this matters. So you see us go clockwise here. We went AF, FB, and around clockwise. And this equation will hold if we go, or excuse me, that we went counterclockwise. This equation will hold even if we go clockwise, but the order must stay correct. So if we go clockwise, that has to be BF over FA times AE over EC times CD over DB. But you can't mix and match the order. You have to either go clockwise or counterclockwise. And if all of this equation holds true, if this equals to 1, then we get concurrent Cevians, and vice versa. So we know if we have concurrent Cevians, then this equation will hold. So we know that this equation doesn't just hold in general, and Cevians aren't concurrent in general. We can see that if we drew another Cevian, like A to here, obviously this line is not concurrent with EB and FC. So it is a special theorem that we have here that is unique and takes a very particular set of circumstances to hold true. And this theorem holds for medians, altitudes, and angle bisectors. all three of those Chevians are all concurrent. So let's go on to proving the if and only if statement.
So to begin proving Ceva's theorem, we first have to prove the forward implication, and then we have to prove the backward implication. So let's get started with the forward implication. So the forward implication states that assuming that the Chevians AD, BE, and CF are concurrent at point O, we prove that the following statement is true. We prove that AF over FB times BD over DC times CE over EA is equal to 1. And it's important to note the order in which these ratios are created. It's significant that they go in a cyclical order. Like any of these ratios can be switched up. You couldn't, for example, say AF over FB times CD over BD. You could, for example, start and go the other way around. You could say AE over EC times CD over DB times BF over FA is equal to 1, and that would be perfectly fine. But for the purpose of this proof, we will go with this equation right here. So to get started, we have drawn altitudes H1 and H2, and these come from points O and points A. So we have H1 and H2. And these are altitudes, so they give us heights to triangles that we will compute the areas of, and these will help us prove this theorem. So first, taking a look at triangle ABD. Using the area that the area of a triangle, the equation that area of a triangle is 1/2 base times height, we know that the area of this triangle is 1/2 times H1 times base BD, and that the area of triangle ADC is 1/2 times H1 times DC. So canceling like terms, we see that 1/2 cancels and H1 cancels. So the area of triangle ABD over the area of triangle ADC is equal to BD over DC. And kind of a similar thing going on for the area of triangle OBD over the area of triangle ODC. We take a look at OBD right here, and its area is 1/2 times H2 times BD, and the area of triangle ODC is equal to 1/2 times H2 times DC. And so similarly, we cancel like terms there. And we see that the ratio between these two areas is also BD over DC. So we're able to conclude that the area of OBD over the area of ODC times the area of is equal to the area of ABD times over the area of ADC, which is equal to BD over DC. So we use this ratio later on to help us prove this forward implication. And we also know that the area of triangle ABD, just by looking at it, area of triangle ABD, if you take away from it this triangle OBD, it leaves you with this triangle ABO. Similarly, triangle ADC, if you take away from it triangle ODC, it leaves you with this smaller triangle AOC. So that's what this says right here. And using these two facts that we know, we can conclude that BD over DC is equal to the ratio actually of these two smaller triangles, ABO and AOC. So once we're able to conclude that, we basically know that similarly, the ratio between AF over FB would be the ratio between triangles AOC and BOC. And that the ratio between CE and EA would be the ratio between triangles BOC and BOA. So these ratios we will use because now we know that this initial ratio that we had up here, AF over FB times BD over DC times CE over EA, we plug in these things that we know now. We know that BD over DC is equal to the ratio of these two, the ratio of the areas of these two triangles. Same with this ratio and this ratio. We plug these into this that we had initially, and we get this expression right here. But you'll notice that there are repeats in the numerators and denominators, so things cancel. So, for example, the area of triangle AOC cancels from the numerator and denominator here. Similarly, for the area of triangle BOC here and here, and the area of triangle ABO here and here. So we end up getting that this whole thing is equal to 1. And that is what we are trying to prove in this forward implication as desired.
All right. So now that we've seen the proof of the forward implication of Ceva's theorem, let's look at the backward implication. So we're going to be starting with our given equation of Ceva's theorem, right? That AF over FB, right? AF over FB times BD over DC times CE over EA is equal to 1. You may notice I've drawn an extra Cevian in here, AD prime. That's going to come into the proof here in a minute. But we're starting with this initial equation. We want to prove that the Cevians are concurrent. So I drew AD here, obviously, not concurrent with these other Cevians with FC and BE, because we want to prove that if the equation holds true, that it will be concurrent, right? So I guess that'll make more sense whenever we go into the proof. So we're going to have line segment AD prime go ahead and satisfy Ceva's theorem by having it be concurrent with FC and BE. So we're saying that point of concurrence is at O. So FC, EB, BA, whatever you want to call it, and AD prime are all concurrent. So we know that their relationship satisfies Ceva's theorem. So we know that AF over FB times BD prime over D prime C times CE over EA is going to be equal to 1, right? And again, we're starting with the given up here that AF over FB times BD, not BD prime, but BD times DC, or over DC, excuse me, times CE over EA is equal to 1. So that's the given. So we have two things that are equal to 1 here. So we are basically going to set those equal to each other and get rid of like terms. So we have AF over FB on this side, AF over FB on this side, CE over EA on this side, CE over EA on this side. So we're left with this equation right here. BD prime over D prime C is equal to BD over DC. So BD prime over D prime C is equal to BD over DC. Now, if you're looking at the picture, they don't look very equal, and that's by design. We want to show that in order for these to be equal, right, in order for these ratios to be equal here, that AD prime has to coincide with AD. The AD has to lie on this concurrent, has to be concurrent with these other lines here, these other Chevians. And that's true if this equation holds. So, and it kind of makes intuitive sense if you're looking at it, that if we're talking about the ratio between this area, line segment and this line segment being equal to this line segment and this line segment, that these points D and D prime have to be the same point. And that makes intuitive sense, but we'll go into a little more formal of a proof here to explain that. So we can make the equation, we can create a function that basically defines where point D is. So if we're looking at just right now B to D prime to C is our line segments that we're looking at. So let's make B to D prime, and let's label that X. And then, so what's the rest of this space going to be? Well, if we're calling this entire line segment BC here, let's call it A, right? Little a. Then the rest of this is going to be A minus X. So this part here is going to be A minus X. So the ratio between this part and this part we can write as a function, X over A minus X. So what we want to prove is that there are no two different X values that will give the same output, right? The same ratio. So X refers to how long this space is here. So we can't have BD prime and BD give us the same ratio, right? There's only one X value. Basically, we're saying this is a one-to-one function. So how are we going to prove that? We're proving that it's monotonically increasing is another way to explain that. So say we had an X value of 1, right? And say A is equal to 4. So we have 1 is our X, 4 minus 1. All right, that's going to be 1 over 3. And then we make X2, right? So let's try X2. Here we're going to have 2 over 4 minus 2. Now, that's going to be 2 over 2, right? That's going to be equal to 1. And if we keep doing that, we can do 3, and that's going to give us 3 over 1, right? That's going to be 3. So we see it's increasing. 1/3, then it goes to 1, then it goes to 3. So we already get, in kind of, we're kind of seeing that it's increasing, an increasing function. But to prove it, with a little more rigor, we're going to take the derivative. We're going to take this function and take the derivative of this function. And if the derivative is positive, we know this function is going to be monotonically increasing. So the derivative of this is going to do the quotient rule, right? So the derivative of X is equal to 1 multiplied by the derivative of the denominator, which is going to be, or excuse me, not by the derivative of the denominator, just by the denominator, which is going to be A minus X. And we're going to subtract the derivative of the denominator, which is going to be -1 times the numerator, which is X. Right? And that's all going to be over the square of the denominator. A minus X squared. Right? And we do some simplification. So we're going to have let me undo it down here a little bit. a minus x, minus a negative, so it's going to be, here's negative x, so minus negative x is going to be positive x, so plus x, which is just going to be equal to a on the numerator. So in the denominator, stays the same. It's pretty much as simplified as we can get. A minus x squared. And we can see this is going to be positive because a is going to be positive. It's the length of the entire side. So our side is definitely going to be greater than 0 for a triangle. And then this a minus x is always going to be, a minus x squared is always going to be positive because it's a square. Right? So when you see that this whole derivative is going to be greater than 0 no matter what, for any triangle that we have. So we know that this function is monotonically increasing, which means it's a one-to-one function. So we know that there are no two x values, which means there are no two lengths of this here, of b d prime or b d, that can give us the same ratio here, b d prime over d prime c or b d over dc. Right? There are none that can give us the same ratio. So we know that if b d prime over d prime c is equal to b d over dc, that the d prime and d have to be the same exact point because this is a monotonically increasing function. So therefore, since this equality is only true if d and d prime are the same point, we know that a d here has to be the same as a d prime, which, well, that's a little messy. But we know it has to be the same as a d prime, which we have started with is concurrent to BE and FC. And therefore, the backward implication of Ceva's theorem is proved. And that's the proof of Ceva's theorem. I hope you learned something. Have a great day.